to start up the panel discussion, today's panel discussion for the panel number 1. And so what I'd ask the panelists to do is kind of go down in order here, and if you can introduce yourself and give a kind of 1 minute a synopsis of what your talk was about, and then we'll discuss it. And if you have questions for the panel, please put them in the Q&A or in Slack. And panelists, if you have questions for the other panelists, you've got the mic, so you can just ask them out. All right, thanks. Andrew, do you want to start?
Okay, great. So you can hear me? Yep. So hi everyone, my name is Andrew Cheek. I'm a postdoc at CP3 in Belgium. And my talk was about analyzing the angular power spectrum and how it's going to allow neutrino telescopes such as KM3Net to make constraints on dark matter annihilations more robust against the choice of dark matter halos. I then went on to talk about particle physics models that these kind of neutrino telescopes will be able to uniquely probe. We try to keep things simple, but we also stressed the complementarity between neutrino telescopes and other searches, such as gamma ray telescopes and direct dark matter detection. Thanks.
All right, Ning Chan?
Yeah, sure, thanks. So I'm Ning Xiang Song, a postdoc at Queen's University, and my talk is about the constraints on GV2TeV in elastic dark matter. And this kind of dark matter are special because they may evade the search at the direct detection experiments because of the kinematical limit. So we looked at such dark matter candidates in scintillating bolometer experiments and gamma ray searches, which can be sensitive to dark matter induced excitation. And these experiments are sensitive to high energy deposition, and these target nuclei are very heavy. So with these experiments, we can push the constraints on inelastic dark matter to the mass splitting of 640 keV beyond the reach of direct detection experiments like Xena and CREST. That's it. Thanks.
All right, Robert.
Hi, everyone. So yeah, I'm Robert Ward. I'm a third-year PhD student at the University of Birmingham in the UK. So I've presented a talk for this conference on behalf of the NewC collaboration. We're searching for light dark matter with spherical proportional counters. So we're trying to look for it with, via nuclear recoil using very low event detection thresholds. So my talk sort of covers the prototype detector and the initial results of this, and assessing the relevance and searching for these light dark matter candidates. And then talk about some of the developments going into the current generation detector called Snow Globe at the Neutrino Observatory in Canada. And then then talking about future developments and how we can reach further, better regions, further down in phase space and stuff, with the future detectors. And yeah, so sort of gives an overview of the collaboration and what we're aiming to do.
Thanks, Sam.
Hi, my name is Sam Whitty. I'm a postdoc at the Grappa Institute in Amsterdam. My talk was on axion photon conversion in the magnetospheres of neutron stars, in particular how we can use radio telescopes to look for narrow spectral lines arising from this process. And this is a field that's been pushed significantly in the last 2 to 3 years, but it's also a field that's sort of been riddled with a large number of uncertainties. And so my talk was on recent work that I've done with my collaborators in Grappa and also in Stockholm on trying to improve the robustness of these searches, in particular accounting for things like refraction or reflection of radio photons, accounting for the proper anisotropy of the plasma distribution in the conversion probabilities, accounting for suppressions of the conversion probability due to refraction of photons and absorption of photons due to Landau levels. And so this is sort of the first step in trying to make these radio searches truly robust in some sense as far as indirect searches for axion dark matter go.
Great, thanks. Simon.
Hi, my name is Simon Viel. I'm an assistant professor at Carleton University in Ottawa, Canada. I'm the analysis coordinator for Deep 3600. So here I presented our latest result. Deep 3600 is at SNOLAB. It's been operating since 2016, and by now we've released our first year dark matter search results with world-leading sensitivity on a liquid argon target. And now we have the program of upgrading the detector. The detector is now empty of liquid argon. We're performing upgrades in the neck region of the detector, where some backgrounds were seen. We're also improving the filtration system to get rid of trace amounts of dust. So we'll take data again with much improved sensitivity starting in 2022. And the long-term program for WIMP detection on liquid argon is the DarkSide 20K experiment. We're working as part of the Global Argon Dark Matter Collaboration on the DarkSide 20K experiment. And then the plan is to come back to SNOLAB for a 400-ton experiment called Argo.
Great, thanks. Viviana.
Yes, sorry for the delay. I'm Viviana Niro. I'm a recurring individual fellow at EPC Laboratory in Paris, and in the talk I presented some prospect for neutrinos from galactic sources. I mainly focus on galactic sources that have been recently revealed by the Hawke telescope. I presented prospect for neutrino from neutrino telescope like ChemTreeNet and IceCube. In particular, I consider a specific source that is called J1825, that is one of the most luminous in the Northern Hemisphere, and I presented prospect for the ChemTreeNet detector, and I showed that in 10 years a 4 to 5 sigma significance can be expected. For this particular source, we also use the information from the Fermi-LAT data. Moreover, I present some prospects for other galactic sources that have been revealed again by the Hawke Observatory, and that can be seen with neutrinos by IceCube. In particular, the sources J1907 and J2019, and that they can be seen in 3 sigma in the upcoming 10 years. And moreover, I present the prospect for other 2 sources, J1857, for which IceCube currently report an excess of neutrinos, and the RxJ J1713, that is a good candidate for ChemTreeNet. So practically all the sources are galactic, have been revealed by different experiments, in particular recently by Hawke, and they can be seen in neutrinos if they are if the emission of gammas is hadronic, of course, by ChemTreeNet or IceCube in the upcoming 10 years. Thanks.
Thanks. So a question in from Slack for Andrew. And when you ask questions, please ask, let me know who I'm addressing it to. So thanks. For Andrew, is kinetic mixing considered in your secluded LMU tau scenario? And do CMB constraints apply here?
Yes, so the short answer is no, they weren't considered for this paper, and what I show in the page 6.4. However, they should be considered, and but we basically neglected them because the branching ratio for this light mediator is around 2 × 10⁻⁵, as opposed to like something very close to 100%. So on to the neutrinos, so that branching ratio to neutrinos should be approximately equal to 100%. And the CMB constraints will come up, but we neglected it. But maybe this line will continue, but like in this pane that we show, it definitely will be there. But we just neglected it, and it's something perhaps we should have done, but I don't think it's going to be competitive to our bounds. So thanks for the question.
Thanks. I've got a question for Ningqian. Are there plans to extend your either the recoil or excitation searches with larger or lower background experiments than the test setups you described?
So the plan, I think in this talk and in our work, what we have explored is that we can really use like some nuclear experiments with scintillating bolometer search, which can be sensitive to high energy deposition and which can use very heavy nuclei, so that for inelastic dark matter scattering, it can be less suppressed by kinematics. So in the future, I think we can reduce on the one side, we can reduce the background so that when we increase the statistics, we can get better and better bound. And the other direction is to look at boosted dark matter, and if the velocity is high enough, so we can better overcome the kinematical limit.
Okay, thanks. I have a question on the Q&A for Viviana. It says it's somewhat tangential to your talk, hopefully not too far off, but do you happen to know if IceCube and KM3net are potentially sensitive to neutrinos that might be associated with gravitational waves from LIGO Virgo? And I guess this ties into the question I had as well, which is what kind of astrophysical objects are these Hawk sources that you're looking at, which might.
Okay, these galactic sources that I presented in this talk are or unidentified, or are, can be supernova remnant associated with molecular clouds, or can be pulsar wind nebula. And so the main point of neutrino telescope would be to test if pulsar wind nebula can emit gammas through an hadronic process and thus emit also neutrino. This or pulsar wind nebula or supernova remnant associated with the molecular cloud. The part on gravitational waves, I mean, when there was the first discovery, I mean, they did an analysis of a joint analysis of with IceCube data. So yeah, but it was not this type of sources.
Okay.
Thanks.
Thanks. A question for Rob Ward on page 7 of your slides. How much does the rise time cut affect the effective volume of your detector? And I guess in particular, because being spherical, the more this cuts, you lose effective volume as R cubed, right?
Yeah, that's right. But it's one of those things where the larger the detector, the smaller this effect becomes. So I don't have a value off the top of my head, unfortunately, but I think we end up keeping like here's a high percentage of the detector effective volume we keep, so like 78%, something like that, possibly even higher. But I'm not, necessarily the I can't say that for certain. But yeah, this is one of those things we're looking at with the simulation to try and understand exactly how the rise time corresponds to the radius of the initial event. So this is something that has been developed. So if you go to slide 12, I believe. Yeah, so for instance, you have a very clear. So the plot on the right shows you the rise time of the event. So the darker it is to show the rise time, the more yellow is, the higher the rise time. So you sort of get an idea of, you can clearly see the correspondence between radius and rise time. So apologies, a bit waffly, but we keep most of the fiduciary volume, and the larger the detectors, the more you keep essentially. So, but yeah, this is one of the things we are looking at with the simulations and understanding.
Okay. The question from Slack, a basic question for Sam. Could you elaborate on the astrophysical constraints you refer to on page 2?
Yeah, of course. So this was in reference to sort of what the conventional mass range for the QCD axion dark matter would be. And I had said that if you want, in most models, if you want the axion to constitute the entirety of the dark matter, you need to have a mass larger than about 10 to the minus 6 to avoid overproduction. And you typically want a mass less than about a few times 10 to the minus 3 eV to avoid astrophysical constraints. And these constraints are predominantly, I think the most stringent ones are coming from the fact that axions will prevent helium burning in stars. And so they will essentially dissipate too much energy in the central region of stars, and the mass with the conventional coupling for the KSVZ or DSVZ models would forbid the helium burning. Yeah. There are also constraints from Super 1987A and some other constraints that are astrophysical constraints in this larger mass region as well. But I think they're subdominant by a factor of a few.
A question for Simone. Which of the backgrounds you've explained worry you the most when you unblind your remaining data?
Right now it's the dust background. So if you go to the slide about this, forget the number. $15. So this is the latest background we've identified in our data set, where the track length in liquid argon of the alpha, because there's some track length in the dust particulate, that doesn't generate scintillation light. So there's much lower scintillation light that's being produced there compared to a simple atom in the liquid argon. And some of that scintillation light is shadowed. So this is really consistent with the signal because it's an alpha that occurs right in the center of the detector. The signature is close to what you'd expect from a WIMP nuclear recoil in terms of energy, in terms of reconstructed radius, and so on. So we are working on discriminants that are dust specific, in particular a neural network that might have some promise there, but it's very hard. I would say that's what's delaying our analysis of the full data set 2016 to 2020, trying to find a way to deal with that and retain sensitivity to WIMPs. And so that's why in the hardware upgrade, we're looking to remove that in situ. It's also, I would say, a warning for future detector development to use in the process systems a filter that with a smaller mesh. So ours let particulates 50 microns in diameter and smaller through. Sub-micron would have avoided that problem.
All right. Thanks. A question for Andrew on slide 6, which actually refers to this stuff in Anna's fantastic talk earlier, the dark matter distribution in the galaxy. So a big part of why this would affect the sensitivity of direct, annihilation WIMP detection is because denser areas you get rate squared because things annihilate more, right? But I'm curious how using an APS dodges this kind of first order density problem. Why does that help so much?
Yeah, I think I won't be able to give you like a very satisfactory answer to this, but as far as I understand it, I think it's because we're looking instead of just the center of the galaxy, where we're extending our field of view, and we're also correlating signals across the whole sky. I think that allows you to smear out potential to smear out such a great dependency on the fact that one of your halo models is highly peaked and one less so. Obviously, using the APS, the angular power spectrum, means that your limits or your sensitivities or your interpretation of your data is going to be weaker than if you were to assume the most sort of optimistic or most densely sort of packed dark matter halo. But because we don't know what the dark matter halo looks like, but we feel like analyzing the neutrino sky in this way is better for kind of like giving people a sense of the actual picture of what could be going on.
Yeah, thanks. Had a question for Sam. So I was impressed by what a whole lot of really careful work it is to get to the observables, to get from the naive sensitivity to the how we thought of things sensitivity. But one thing I was having a hard time making a connection for was how does that compare to terrestrial axion searches in terms that use lower B fields? You had kind of a limits plot, and I wasn't clever enough to write down the slide.
Sure. Yeah. I mean, I think that's the very last slide of my talk, if
Yeah,
you want to pull it up. So I should emphasize that radio searches are going to be sensitive to masses between, say, 100 megahertz and say maybe 100-ish or hundreds of gigahertz range, depending on the radio telescope that you can use. The projections I'm putting here are for the square kilometer array. And the blue regions right here that are the ADMX limits. And these aren't the exact ADMX limits. They're the ADMX limits that are smooth. In reality, there's more jagged and holes in these limits. Coming from the fact that they are a scanning-based experiment. So they have to scan for resonances, and sometimes they have holes from the fact that they don't want to scan a particular range. So the ADMX is certainly going to cut deeply into the QCD axion parameter space. That's for sure, but it takes them quite a bit of time since they do have to do the scanning process. I think a key point to emphasize is the complementarity, as always, between direct and indirect searches. We don't have to do the scanning. We have a natural way to scan just by the fact that we have a radially dependent plasma frequency. So we're scanning many resonances at the same time. And using different telescopes, using future telescopes like HERO, we can also push to lower frequencies where ADMX will never be sensitive, and higher frequencies where ADMX will never be sensitive. There are hopes to probe the higher mass region with direct detection experiments like MAD-MAX, and the lower mass region with experiments like DM Radio and Abracadabra, which have now merged, I think, to a single experiment. But again, these are always going to be complementary searches, in particular because it takes two of these things to confirm not only the detection of a new particle, but also that this is dark matter. And sort of the final key is that, of course, if we detect a narrow spectral line from this process, we can directly infer the mass of the axion, meaning we can go to ADMX or MAD-MAX and say, go drill your experiment and spend a lot of time searching at, say, 5 times 10 to the minus 5 EV. And they will do that in the course of a day or two. And after that, they will have killed through the QCD axion line, and they will know exactly whether or not that hint that we observed was true or whether it's false. So I think that that's really a key, is not just the a juxtaposition, but also the complementarity of the two.
Yeah, thanks. Question for Viviana on slide 16. You have several epsilons, the efficiencies in your integral for how do you turn the gamma rays into neutrinos. Like 0.57, 0.72, for example. How firm are those numbers?
So I mean, one is the visibility of the source, because this source is visible by ChemTreeNet. So ChemTreeNet is planned to be here in the Mediterranean Sea, and so the source will be visible only a certain fraction of time, and this can be calculated, and for this particular sources is around 60% more or less. The other epsilon is 0.72, is just a factor that is present for if you assume a Gaussian distribution for the gamma emission, because even if you have a point source, okay, in this case it's not a point source, but it's an extended source. But in any case, for a neutrino telescope, there is an error due to the resolution and the extension, for which the source will be seen as extended, and so you will not take all the flux that you have in gamma rays. You will not be translated to neutrinos, but there will be if the distribution is Gaussian, you will have a certain percentage that in this case for a 2D Gaussian is 72%, that the gamma ray signal is translated in neutrino signal for an effective angle of 1.6 square root of extension plus resolution. Essentially, it's coming from a two-dimensional Gaussian, considering that both the source is a Gaussian distribution, and also the resolution, and then you sum also the resolution of the instrument. So the 72% is within this angle, sigma effective.
Okay, and so those are both not very model dependent at all. Is the point?
Dependent from what? No, this it depends on the morphology. I mean, for a two-dimensional Gaussian, you have that the 72% is within this effective angle, 1.6 square root of the extension plus resolution, and this is just a mathematical fact. If you assume that you have a Gaussian in two dimensions. If it is not Gaussian, for example, we do a case where it's not Gaussian, then you can assume that you take all the gammas that you have in neutrinos, all the gamma emission will be translated in neutrinos directly, so that you will not have any reduction factor. You can assume that you have a different morphology of the source, not Gaussian, and so you assume that you take all the flux. So we do a case like this because we consider that for a particular source the morphology is not Gaussian. So we assume that over a certain angle all the gamma ray flux can be translated in neutrinos. So you will not have this 72%, but this epsilon will be 1. So it's an assumption of a different kind of morphology where you assume that all the gammas that you see directly translate in neutrinos, like it was like a box. The visibility depends on the position of the detector and the position of the source. So for ChemTreeNet, these sources are not always visible because ChemTreeNet is in the Mediterranean, so the zenith angle of the source changes with time. For IceCube, a certain zenith angle is fixed because it's the South Pole, so it doesn't change with the declination of the source corresponds to a specific zenith angle in the detector. So it's more simple.
Okay, thanks. All right, yeah, I understand now. But time for a final question here in the Q&A from Dorian Emerald for Andrew. One, would boosted dark matter models affect the projected angular power spectra you showed in the signal hypothesis and hence your analysis?
I think yeah, I'm not too sure. I think naively I'd say yes, but especially if it's your boosted dark matter is, well, no, actually, no, I'm not sure if I understand the question, because usually in my experience, boosted dark matter models are usually considered in direct detection experiments where you're interacting with. Also, I guess you could have. Yeah, sorry, I'm thinking out loud here. So I guess you could have boosted dark matter from the galactic center, and then that could disperse, and that could produce some kind of neutrino signal further from the center. So I guess in that case, you would have a difference. But yeah, I'm not too sure. We can talk about it on Slack later if you want.
Yeah, and particularly because there's a more complicated follow-up question for that. So that'd be great for Slack of course, all the questions will be moved to Slack, so you can elaborate on them or ask more questions or provide links or whatever it is else you might want to do there. Thanks. That brings us to the end